Today we are going to discuss the Chomsky hierarchy. In the last lectures, we have seen various grammars of different languages. Now we see, according to the production rules of the grammar, how Chomsky has given the classification. 1956 and 1959, Chomsky has given various research papers, and on such papers, he has discussed the classification of the languages. So he has basically given the four classification, which be popularly known as type 0, and means grammar is type 0 grammar, or we have the type 1 grammar and type 2 grammar and type 3 grammar. So Chomsky has given the four classes of grammar, and accordingly we have the four classes of language, and these four classes of language is actually referred as Chomsky hierarchy of languages, or corresponding grammar we can say the Chomsky hierarchy of grammar. So how Chomsky has categorized the grammar into the four groups. So actually scientist is Noam Chomsky. According to the production rules of grammar, Chomsky has seen that some grammars he has given, some grammar he found that such grammars are having the more expressive, means they have more capability to do the job as compared with the some restricted one. So when you move from top to bottom, if you go from top to bottom, then you will find that type 0 grammars are more general grammar. You can see these are the most general grammar. And once you move down, you will find that most restricted grammar. Most restricted. So you can say that type 3 is the most restricted grammar, whereas type 0 is most general grammar. And as you move down, you will find that type 1 is more general as compared with type 2, and type 2 is more general as compared with the type 3. So type 3 is the most restricted grammar, and means you can say that these are the grammars which have more expressive power. So type 0 grammar is having the more powerful capabilities. You can say most expressive. Okay. And once you move down, you will find that these grammars having the less expressive capability. Less expressive means you have some, with the help of the type 3 grammars or type 3 languages, you can do some small job as compared with the type 0 grammars. So Chomsky has given these four types. So whenever you talk about the learning of such grammars, then you will find that learning the type 0 grammar you requires more skills as compared with learning the type 3 grammars. Learning is difficult whenever you go up to the Chomsky classification, then learning type 0 grammar is more difficult. So learning difficult. And whenever you move down, you will find that learning comparatively, relatively easy. So once you talk about the type 3 grammar, learning type 3 grammar is more easy as compared with learning type 2 grammar. Learning type 1 grammar is more difficult as compared with type 2, and learning type 0 is most difficult for the computer science. So even you will find that learning type 2 grammar is itself more difficult, and we don't have algorithm presently for learning type 2 grammars or type 2 language without any heuristics. Whereas we have some algorithms available for learning the type 3 grammars. So now you may have the questions. How, which kind of grammar we refer as type 0 grammar, or which one is type 1, which one is type 2, and which one is type 3 grammar. So according to the production rules of the grammar, we will see that some grammars have very simple rules like type 3, and some grammar have very general rules like type 0. So according to the production rules of the grammars, we we will see that the different types. So let us see what kind of production rules we require for being the type 3, what production rules we need for the type 2, and what production rules we have for the type 1 and type 0. You see the Chomsky hierarchy, then you will have this. Here is the type 3. So this is the bottom, and you have the type 3. And if you go up, then this is the, we have the type 3 at the bottom. As you move up, you will find the type 2. And then if you further going up, then you have type 1. Then here you are having the type 0. So whenever you go for the type 3, type 3 grammar, then the name of the type 3 grammar is regular grammar. And corresponding language, we have the regular language. The production rules of type 3 grammars, every production rules of type 3 grammar will be of in either of these two forms. Either A derives small a, means this is the alphabet, means we can say that this is the terminal. Terminals, non-terminals can derive terminal and non-terminal, or non-terminal can derive only the terminal. Length of the right hand side string is either 2, and if it is 2, then first one should be the terminal and second one should be the non-terminal, and if it is 1, then it must be the terminal. So if every production rules of the grammar is of having this any one of these two forms, then you can say that this is the type 3 grammar. So we have seen various grammar for different language. Can you identify which one is the type 3 grammar? This language we have considered when you have observed the grammar for this language. And you can, if you see in your notes, then you will find that production rules of this grammar is either you have in the form of either in this form or in this form. So A and B can be any non-terminals. We started from S derives B and S derives B as like, and you have started S derives A, then you have the A, then further for the A like this. So every production rules of this grammar is having these two forms. So you can say that this is the regular grammar, this is the regular language, as you have the regular grammar. And this is also one way to prove that whether the language is regular or not. Somebody may ask you that, how can you prove that the given language is regular? You are given some language like this, and you may be asked whether this language is regular or not. What you need actually, you need to construct the grammar for this language. And if you are able to construct the grammars with these kind of rules, you have either this form of rules or in this form of rules, then you can say that, okay, this is the grammar which is the type 3 grammar, and it is the regular grammar, and hence the language generated by this regular grammar is regular. So the given language is regular. So this is also one way to prove. You have seen in case of the type 3 language, what conditions of production rules are there. You have left side you have only one non-terminals, and right side you have the working string, which is first one is the terminal and next one is the non-terminal, or you have the non-terminal, single non-terminal in the left, and in the right string you have only the terminal symbol. So this is very restricted one. The length of this is maximum 2 or minimum 1. It cannot be null. And length of the string from the left side is having only one non-terminals. So that's why this is most restricted grammar in the Chomsky hierarchy. And this is one of the simplest one as compared to if you move up. Now the question is this, which model of computation is suitable for this language or this kind of grammar? So here we are going to study FA. FA means finite automaton. So we are going to study finite automaton. So finite automaton, this is the abstract model of computation, and this model is accepting the type 3 grammar or type 3 languages. This is one of the simplest model of computation suitable for accepting the type 3 language. Now, whenever you move to the type 2, the production rules of the type 2 grammar will be of this form. A derives alpha. Here, A is what? A belongs to the variable, means A is any non-terminal, okay? And alpha is the string of terminals or non-terminals both. So you can say V union sigma clean star. So if the every production rules of the grammar is of this form, A derives alpha, then you can say that this is the type 2 grammar. So here you can observe the type 3 production rules, and you can say that the type 3 production rules is also of this form, A derives alpha. Here left hand side you have only the single non-terminals, and right hand side here the restriction is maximum 2 or minimum 1. But in case of the A derives alpha, the right hand side string can be of any length, because alpha can be the string of terminals and non-terminals both. So this can be null also, but here you can't be null. This can be null also, or this can be, the length of this alpha can be more than 2 or more than 3 or 4, 5, 6, 7, 8, anything. You don't have any restriction in the alpha. Only the restriction is there. The left hand side you have the not one single non-terminals. So A derives alpha, and you can, if you see the type 3 production rules, then you will come to know that all these type 3 production rules is also in this form. A derives alpha. So you can say that these two forms of rules, A derives AB and A derives A, these are the special case of the A derives alpha. So since this is the special case, that's why it is inside of the type 2. So here if you have the grammar rules where you have A derives AB and A derives A, then these are the type 3. Otherwise, if your grammar contains the form of rules like A derives alpha, if you have in your grammar, if you have all such rules of like this, but at least one such rule will be there, which is not here, but it is in this form, then you will say that this is the type 2 grammar. The type 2 grammar is known as the context-free grammar, and which is in short, you can say CFG. So this is the context-free grammar. Context-free. So context-free grammar, you can say CFG. And the corresponding language is known as the C context-free. So you have the context-free language. And in short, you can say that CFL, context-free language. So language represented by the type 2 grammar is context-free, and the corresponding language you will see this is the CFL. So now you can easily observe that A derives alpha and you have A derives AB, and the right hand side string alpha can be of any length, and hence this grammar is more expressive as compared with this, because here you have the restriction of length 2, but here you don't have any restriction. This means you can do more complex job with the help of type 2 grammar or context free grammar. So out of the grammars we have discussed for the various languages, which grammar is satisfying the rules for the type 3, sorry, type 2. So which one is context free? CFG. And so you might have seen the language we have discussed. L is the set of string X, which is taken from the sigma star. Sigma star is some alphabet, sigma is some alphabet. So condition we have x is equal to xr. So this is what? This is the language of palindrome we have seen. So when you go for the grammar for this language, then what kind of grammar we have here? You have seen the grammar like S derives null, then S derives A, S derives B, assuming that sigma we have A and B. So you can see rules like this. And also you have the rules like this. A as A and S derives B as B. So these kind of rules you have found in the grammar or the language of polynomial when you have the alphabet A and B. So either S derives null, this is the string of length 0, or S derives A, or S derives B, or S derives first should be A, then last must be A, and first B, then last must be B, you are in theory. And then see the form of rules here. Every rules of this grammar is of this form. You can easily verify. Left hand side you have only single non-terminals, and right hand side string is formed by combination of the V union sigma k. So right hand side string is the string of terminals and non-terminals both. And it can be 0 also. So you have seen that the length is 0, and here the length is 3, and here you have the length is 1. And if you can observe these two rules, then these are the type 3 rules. You can verify in the type. So this is the type 3 rules. But when you go for these and these rules, then you will not find in the type 3, but these are in the type 2. This is also in type 2. So what is the type of this grammar? This is not the type 3 grammar, even it contains two rules of type 3, but it has also the rules which is not in the type 3, and hence the grammar is type 2. So whenever you have the rules of the grammar in say I denote the type where I can be equal to 3, 2, 1 and 0. If your grammar contains the rule contains the rules of type I, and also it has also some rules in the type I minus 1, then the resulting grammar is type I minus 1. So here you can see some rules are in type 3. So here I is equal to 3. Some rules are type 3 and some rules are type 2. Hence this is the type 2 grammar. So grammar for the language of palindrome is satisfying the condition A derives alpha. And when A derives alpha, and this is the grammar which we see as context-free grammar. And why it is named as the context-free? As the name suggests, context-free means replacement of the variable. It does not depends on any form of the context. So whenever you see as, you are free to replace with either A or B or in this form or in this form. You don't see any context. You don't bother about left side or you don't bother about right side because there is no such symbol. So this is the context. The meaning remains same. So that's why this grammar is referred as context-free grammar. And the language, corresponding language is context-free. So which kind of model is suitable for this grammar, this language? The abstract device for accepting the type 2 grammar or type 2 language, or you can say context-free language is PDA. PDA. So PDA is the generalization of the finite automaton. What we mean by the PDA? This is the push down automaton. Push down automaton. So this is the, so you can remember here I'm writing the automaton. So once you write the automaton means I'm talking about the single machine. Once you say automata, it means more than one. So PDA is the device abstract model of computation which is suitable for the context-free languages. So this is the type 2. When once you move up, then you will have the type 1. What kind of rules should be there in type 1? The production rules you will find here is like this. Alpha derives beta. Now, alpha and beta is what? Alpha and beta can be any string consist of ternals and non-ternals both. So you can say V union sigma k star. And alpha contains a variable. So alpha must contain at least one variable because this is the string which is in the left. So alpha is the left side string and beta is the right hand side string. So alpha contains a variable. At least one variable should be there. Then you can replace the variable into the form of some string and you are going to obtain the string beta. If you have only the terminal symbols in this string, then this is the constant you can't change, then alpha and beta will be same. So for the replacement, if you want to apply the production rules, then actually alpha contains at least one variable. So form of production rules in this grammar is like this, alpha derives beta. And one more condition here is the length of beta. The length of beta is greater than or equal to length of alpha. So right hand side string length will be at least alpha. So it means you cannot use the production rules of this form. Of the form like you have A derives null. Why it is so? Because if this is alpha and this is beta, then length of this beta is equal to 0 and length of alpha is equal to 1. And what this says that length of beta must be more than or equal to length of alpha. So such kind of production will not be there. Except these, every form of productions are there. So you can see here, alpha derives beta. These are the more general rules as compared with the A derives alpha, where these are the special cases where you have only the one non-terminal here, means one variable here, and here you can have many variables here. You are not restricted with one variable. You can have more than one variables or variable and terminals in combination. So these are the more general rule, alpha derives beta, and these are the special case of these form of the rules, and hence that's why these are the type 2 is inside of the type 1. So type 2 type 1 is having the more general rules as compared with type 2. The language of type 1 is or grammar type 1 grammar is referred as the CSG, which is the context sensitive grammar. This is known as the context sensitive. So context sensitive grammar, and you insert, you can say that CSG. So you can write here CSG, context sensitive grammar. And the language, corresponding language is known as the CSA, which is the context sensitive language. You can refer as the context sensitive language. So here the type 1 grammar is context sensitive and corresponding language is context sensitive language. So you will find here all context free languages are within the context sensitive except your language, context free language does not contain the null string. It should not have the null string. No. Except all such language, if whenever your context free language is not containing the null string, then you can say that okay, this is also the context sensitive because this is the special case of the context sensitive. So as the name suggests here, context sensitive What we mean by the context sensitive means generally when you go for the context sensitive productions, then we have here you can write more general like this alpha a beta can be referred as alpha x beta. So more suitable form you can write like this. So here alpha and beta can be the string of you have the terminals or non-terminals. So here alpha and beta can be the string of terminals and non-terminals, and alpha beta has no restriction that they may contain variable or they may not contain variable. We don't because a is the non-terminal here. Remember that a is the variable, and here x is the any string. So x can be any string which is in the combination of terminals and non-terminals both, or it contains the only terminals, but x must not be the string x must not be null. So x cannot be null. If it is null, then you can easily see that this can violate the rule. Length of beta must be greater than or equal to alpha. We have to ensure, and hence x cannot be null. So see what is the intuition of these rules. What that's and then you can easily verify this is the context sensitive. The intuition is actually you have the rules of this form. It means you are going to replace the variable a. Non-terminal a is replaced with the string x. But directly you are not able to replace this a with the x. The meaning of a is x if and only if the left side of a is alpha, this is string alpha, and right side is beta. Means left context is alpha and right context is beta. If left is alpha and right is beta, then only you are able to replace this a with x. But if you have in some working string, you will find the intermediate strings like this. A is the non-terminus and AB. Then you are not able to replace this A with X. Why it is so? Because left hand side is alpha. So you have to specify what alpha is here and what beta is specific. In case of the specific production, you have to specify what alpha is there and what beta is there. And whenever you see left context is this and right context is same, then only you are able to replace with X. So that's why this is the context free. The meaning of this, the meaning of A is X if and only if the left context is alpha and right context is beta. We have seen the grammar for the language as AN, BN, CN, and n is greater than or equal to 1. Okay. We have seen the grammar for this language, and you can remember I have given the production in the form like this. Once we start the grammar, we have seen the production rules. We are the first symbol of we have written H and it is BC S1, and you have the either HBC, and then we have seen that S1 derives ABC S1, or you can just say ABC, and here H we have replaced H with small, and remaining strings. Once you see the remaining productions of this grammar, then you can easily verify that every production rules is of this form. Alpha derives beta. Now we don't have any restriction in the left hand side and in the right hand side. Alpha can be any string of terminals and non-terminals both, and it contains at least one variable, and you can see that the left hand side non-terminals having this form. And you have also seen the production rules where you have seen that CA is replaced with AC like this. So here you have the length of the left hand side is 2 non-terminals. So this is the string of non-terminals only. So this fit in this form. And every production rules, if you see, then you can observe easily that the length of beta is more than or equal to length of alpha. So here you can see length of alpha is 1 and length of beta is 1. So this satisfies. This also satisfies. Length of beta is either more than this length. Okay. So length of beta can be more than or equal to alpha. So this is the grammar for the language A and B and C N, which is, you can say that this is the context sensitive grammar. So this is the type, this is the, you can say, this is the type 1 grammar. We have seen the type 1, and what is the model of computation for this case? LBA. So linear bounded automaton. Linear bounded automaton. So device for accepting this language abstract model of computation is LBA, linear bounded automaton. Now once you move further, then you have the type 0 grammar, and the form of the production rules of this grammar is like this: alpha derives beta, and there is no restriction at all. But no restriction in the length of alpha or length of beta. Here you have, in the case of the type 1, we have seen that length of beta must be greater than or equal to length of alpha. But in case of the type 0 production alpha derives beta, we don't have any restriction. Alpha derives beta, alpha can be anything, beta can be anything. Condition is that again alpha and beta both are a string of terminals or non-terminals both. Sorry. String of terminals or non-terminals both, and alpha contains a variable, because this alpha is the left hand side string and you must have the variable. It means you are going to replace the variable with some strings, and you have obtained the string beta, and this can be anything. The length of beta can be more as compared to alpha, or length of beta can be less as compared with alpha. There is no restriction at all. So here you can see that this is the special case of alpha derives beta. Why? These are the special case. Why? Because length of beta here you have the length of beta is more than or equal to length of alpha. But here you can have any gender. So these are the special case of this. But in case of alpha derives beta, beta can be anything. Beta length can be less than alpha, or it can be more than alpha. So this is, and left hand side is the string of terminals and non-terminal both. So alpha contains at least one variable here, means at least one non-terminal must contains. Then you are able to obtain the beta. If alpha is not having the non-terminals, means not having the variables, then alpha and beta means same, because you are not able to change the string. Then so alpha and beta you mean same. So left hand side you must have the at least one variable. So when you go for the grammar for type 0 grammars are known as phrase structure. So you have the phrase structure grammar, or unrestricted grammar, you can say unrestricted grammar. Okay. So type 0 grammar is phrase structure grammar, or you can say unrestricted. We don't have any restrictions on this. The corresponding language of type 0 is known as the recursively enumerable language. Recursively enumerable language. So this is type 0 represents the recursively enumerable language. And later on, once we discuss the Turing machine, then you will come to know the notion of recursively enumerable language. So like type 1 is the recursive language, and this is the recursively enumerable language. And such grammar is more complex grammar, and this is more expressive and more most general grammar you have without any restriction, and hence with the help of this kind of grammar you can do more complex job. The device, the abstract model of computation of this grammar or this languages, the abstract model which is accepting the recursively enumerable languages, actually the Turing machine, which we denote by writing the TM. This is the Turing machine. Turing machine. So now you have seen the four classes of grammar and associate languages. So type 0 is more general grammar as compared with type 2 or type 1 or type 3. And hence we have the Turing machine here, and Turing machine is the general model of computation. And you can say that these are the some simpler form of the Turing machine. So Turing machine is capable of computing any complex job, means Turing machine is capable of computing any problems for which you can solve, or machine can solve, or a team of person can solve. The Turing machine is also capable of computing such problems. And hence Turing machine is one of the most still is the powerful model of computation, and still there is no more powerful model of computation exist after the Turing machine. So Turing machine is more general model of computation. This is actually the Chomsky hierarchy. The language, as you move up, you will find more difficult, more expressive, more general languages, but you are able to do more complex job. Okay, your abstract model of computation is more powerful. Whenever you go from bottom to top, then here you have the finite automata, and once you go for above, then PDA, and PDA is more powerful as compared with finite automata. When you go for the LBA, LBA is more powerful as compared with PDA. And when once you go for the Turing machine is the powerful model, and it is the general model of computation. And the problem which you can solve, a team of person can solve, machine can solve. The same problem you can also solve with the help of Turing machine. And this is the thesis given by the Alonzo Church. If you can solve the problems, Turing machine can solve the problem. Means the problem is, if Turing machine can solve the problem, then you can say that the problem is computable. Otherwise, for some problems, even Turing machine cannot be applied for solving the problems. Here we have the recursively enumerable language. Once you move up, then you will find here not recursively enumerable language. And for not recursively enumerable language, we don't have any model of computations. Which grammar is type 0 you have seen so far? So again, you have the grammar for the A and Bn. Okay. Here you have the grammar for the A and Bn, and in case of the A and Bn, whenever you have gone the production like this, as derives, what you have done HS1, and S1 we have seen that A, B, C, S1 are A, B, C, and then we have used HA replaced with small a. And here you see that this is not the type 1 rule, because length of this beta is less than this. So, so here every rules of this form alpha derives beta, and there is no restriction of the alpha and beta. Length of beta can be less than this. So this is the actually this kind of grammar is the example of the type 0 grammar. So we will see in the next class. Okay. Till that you revise all such things.